Okay, so regression lines, what are they? Sounds complicated, but actually they're just lines of best fit. A regression line is just a line of best fit through the data. We specifically look at linear lines of best fit, so just straight lines through the data. Just like we look at in pure maths, a straight line, a regression line, can be described by y equals mx plus c. Okay, it's a straight line, so we can find the gradient, find the y-intercept, and we can come up with a regression line between two variables. We can use those regression lines to make estimates of what one variable would be if we know the value of the other. If we know someone's height, can we make a guess at their weight, for instance, if we have a line of best fit? So here's a quick example for us. This is sports-related correlation. I specifically had football in mind for this one. It's possession, which is how much of the time a team has the ball and how many goals they score. Okay, if you have more of the ball, you're more likely to score. Okay, which is why there's a positive correlation here between the two. And we can come up with a regression line between the two of them. And this is actually the regression line. So G is the goals scored. So remember, they don't have to be X and Y. You'll quite often see them as different letters. Don't get confused by that. It's just the thing on the Y-axis, which was goals scored, and P was the thing on the X-axis, which was possession. Okay. So we can use that line to help us come up with estimates of how many goals you might score if you know how much possession you had, or vice versa, how much possession would you have given that you'd scored so many goals. So let's have a look at that. There's our regression line again. Find the goals scored when the possession is 70%. Well, I'm just going to use our regression line. Goals scored equals 0.08 times our possession, which is 70, minus 2. Stick that in a calculator. I get 3.6 goals. Obviously, you can't score 3.6 goals, but it means on average there would be 3.6 goals. Kind of makes sense. If you've got 70% of the possession, you're dominating the game, so you score quite a few goals. Or we can do it the other way around. Find the possession when 4 goals are scored. So G is 4 goals are scored, and we want to find P, the possession. So write out our equation, and we're just going to solve it. So I'm going to do a little bit of rearranging here. Bring that 2 across, I get 0.08, P is 6. P is 6 over 0.08, which is 75%. Okay, so if a team scored 4 goals, chances are they had about 75% of the possession. Okay, so there's an example of how we can use regression lines to make estimates of one variable if we know another. And you can often get asked to do this in exams. And we're going to have a quick chat about interpolation and extrapolation as well, and what they are. I'm going to do that mostly with an example. They're about taking estimates from data and whether your estimate is likely to be any good. So I've taken this from the large data set. There is the wind speed and the temperature, and there tends to be a correlation between them. So as the wind speed gets higher, the temperature tends to get lower, which is kind of what we feel all the time. It tends to be cold when it's quite windy. So I've got 10 data points there, and I've graphed them below. And I've also figured out the equation of the regression line. So the regression line for this is going to be, it's 27 minus 0.62 times the wind speed. Okay, that's our regression line. So we can use this formula to make estimates of the temperature given the wind speed, and make estimates of the wind speed given the temperature. Okay, and that's what we're going to do. So the first one is estimate the temperature when the wind speed is 8 miles per hour. So I'm going to use our regression line. So I get T is 27 minus 0.62 times 8. and that is 22 degrees C. If I have a look at the data, it seems about right. Yes, so 22 degrees C, we can see it's quite close to this point here, somewhere between this point as well. Okay, so it seems to approximately make sense with the data we've been given. Now this is what we call an interpolation. The reason for that is if I look at our data, our data for wind speed goes from all the way from 1 mile per hour all the way up to 24 miles. Now we're trying to make an estimate for 8 miles per hour. That lies within the range. So our data goes from 1 mph to 24 mph. Okay, we're after 8. It lies within the data. So we're making an estimate, maybe, I don't know, around here somewhere, where we're trying to read off the temperature given the wind speed. It's well within our data range. So it's an interpolation. That means we're looking for an estimate within the range of our data. That normally means we can get quite a good estimation, and we can be quite we can be happy with the certainty of that estimate, and that it's likely to be quite accurate. What about this one though? Estimate the temperature when the wind speed is 40 miles per hour. Now when we can do that, so you get T is 27 minus 0.62 times 40. And I'll type that into the calculator, and we're going to get 2.2 degrees Celsius. Okay, so I can get an estimate, but the question is that accurate? The answer is we don't really know, and it's probably unlikely to be, because actually in this case we're making an estimate down here somewhere. We don't have any data for that. It's all the way across here. Very high wind speed, very low temperature. It's what we call an extrapolation. We're extrapolating beyond the range of our data. We don't have any data to prove that that happens. It might be that our regression line doesn't really apply there. So this is our regression line at the moment. It might be that it does this now, or maybe it does this. We don't know that our regression line continues in that way, so we can't be very certain about the quality of that estimate. So an extrapolation tends to be a lot less accurate, because we're using beyond the range of our data to try and come up with an estimate. Okay, so that's the difference between interpolation and extrapolation. Now there's a little bit here about interpreting the gradient and the importance of that. So the example I've got is I've given the regression line between the number of chocolates eaten and the number of students in a class in a given month. Okay, so if I was drawing a graph, this is the number of chocolates eaten, this is the number of students. We've got a line which looks something like this. Now, you might get asked in an exam, what does the gradient mean? Now the gradient of this is 12, because that's the number with s. Think about y equals mx plus c. So the gradient, m, is 12. What it means is, a good explanation is for each additional student, $12 more chocolates are eaten. Okay. If we increase the number of students by 1, we'd end up eating 12 more chocolates. So what it means for us is, on average, each student eats 12 chocolates. Yeah, that's an interpretation of the gradient of that regression line. Or eats 12 chocolates a month. Okay, so it's just a random example, that one. But you can get asked about what the gradient means, and this is where you have to think about the context of the problem as opposed to just the regression line. Think about what we're actually being asked about, the context, and just make sure you understand what the gradient actually implies in real life. It's just trying to get you to understand what these things actually mean. And I said it'd be quite a short one, and that's it. I haven't got an exam style question for you on this one because it was quite short. But if you go on the website at Solve4x, there's still loads of questions on this topic, all the quiz questions and practice questions as usual. And next time, we're moving away from data and onto probability. And the first one, I believe, is looking at Venn diagrams, some of which you'll have seen before, but some of which is new at AS. Thank you very much for watching, and I'll see you next time.